Welcome. In this video, I'm going to do a fun little integral that cannot be done using elementary integration techniques. So this is how you start. To start, notice that we've called our integral I. And so we're going to write a slightly different version of it where we replace the x's with y's and also call it I, because clearly this is the same as this, yeah, except for using y instead of x, but that shouldn't make a difference, right? Okay, cool. Next, and this is really the only inventive part of this solution, is to write I squared. I squared will then have to be the integral from negative infinity to infinity of e to the negative y squared dy times the integral from negative infinity to infinity of e to the negative x squared dx. Cool. And next, we're going to write a double sum in place of the product. And the double sum is going to be from negative infinity to infinity on both integrals, clearly, of e to the negative y squared times e to the negative x squared, and then dy dx. So now you should be a little puzzled. You should be asking the question, how is it that I'm allowed to write in place of what I just underlined this? Well, that's allowed because of this property of sigma. Remember, the very definition of an integral required sigma, right? So any properties that discrete sums have, so does lowercase sigma, which adds infinitesimal things. Yeah? Cool. All right, so that's why I'm allowed to do this. And then next, using exponent rules in here, we can write the following, that I squared is equal to negative infinity to infinity. You get it. And then it's e to the negative x squared plus y squared dy dx. Seeing x squared plus y squared triggers in our memory the polar coordinate lessons we've had, in that x squared plus y squared equals r squared in polar coordinates. And clearly, writing r squared in place of x squared plus y squared allows us to simplify things. And so we like that. And so this is suggesting that we should switch to polar coordinates. In fact, we're going to do that. Now, we don't just replace this with r squared. We also need to replace that and the limits of integration. Yeah? So let's first talk about how we replace dy dx. Remember, dy dx is the dimension of an infinitesimally small rectangle that has dimensions dx by dy, right? Now, the equivalent to that in polar coordinates would be an infinitesimally small wedge, right? Like little wedge right here, little strip like that. And so what would the equivalent to dy dx be in polar coordinates? Remember, in polar coordinates, we have r comma theta, and in rectangular coordinates, we have x comma y. And in polar coordinates, r is how we cover, starting from here going out in every direction, right? And theta is how we cover, through angles, traversing from the positive x all the way around and back, right? That's how we cover theta. So if this is theta here, and I'll write in black so it's distinct. If this is theta here, remember, this arc would have length r theta. So then this small strip of a rectangle, an infinitesimally small rectangle we're talking about, should, since radially out is r, should have dimension dr, and then this change here should be r d theta. I cover this in much greater detail when I do polar coordinates and multivariable calculus, so I'm not going to go through it in greater detail here. This should be enough for you to follow that, the equivalent to that small rectangle in polar coordinates will have to be a rectangle of dimension, and I'll do it right here, I'll do it where? Here, sure, of dimension dr by rd theta. Yeah? Cool. All right, so we figured out our replacement there, but what about our limits of integration? Now, for our limits of integration, notice that negative infinity to infinity for both x and y is telling us to go all the way out to the left, all the way out to the right for x, and then all the way north, and then all the way south for y. The equivalent to doing that in polar coordinates would be to go all the way out radially in every direction. So that's from 0 to infinity for r. And then for theta, to cover the whole plane, we need to go from 0 all the way around and back. So that's 0 to 2 pi. So we figured out our limits of integration. We figured out what we have to do here. So we can now finish the job we started. And signifying the change in polar coordinates, I'll write in a different color. So we'll have, in polar coordinates, still a double sum. But as you see, we have inside e to the negative r squared. And then dy dx has become r dr d theta. And then the limits of integration for r, as I've just said, 0 to infinity. And limits of integration for theta is 0 to 2 pi. And there we are. All we have left to do now is figure out this integral, and we have our solution for this problem, essentially. Well, we'll know I squared, and therefore we know what I will be. Yeah? Cool. So I squared then is going to equal the following now. 0 to 2 pi. I think we're ready to integrate with respect to r, which is taking care of that. And how nice is it that we have that important integration factor r there, so it's simple u substitution, right? And in fact, I'm not going to show you the details of that simple u substitution, and I'm just going to write the answer to this, right? And that should be e to the negative r squared times negative a half evaluated from 0 to infinity. And then, of course, we still have d theta. Now, the details of this evaluation are fairly straightforward, so that too I'm just going to skip. And so if you do that well, you should have 0 to 2 pi of, well, 1/2. We can factor out a 1/2, and it's just going to be d theta. And if I'm skipping over too many details, notice I'll fill you in. If you plug in infinity, you're just going to get e to the negative infinity on that part. That's 0. And then if you plug in 0, you're going to get e to the 0. And so that's negative 1/2. And why does the negative disappear? Because we're subtracting when we're evaluating, right? So that's why the negative from the 1/2 disappeared. So those are all the details that you needed. Okay, cool. And now we're going to write that this is equal to 1/2 theta evaluated from 0 to 2 pi. And if you evaluate that, that should equal 1/2 times 2 pi minus 1/2 times 0, which I won't bother with. And so I squared is pi. And so our original integral that we've been trying to solve is equal to root pi. Isn't that cool? I thought so, and I hope you also thought the same. And keep watching. Take care.